Assalamualaikum warahmatullahi wabarakatuh, and good afternoon to all of you. So I hope you all are fine. Okay, even though maybe some of you are affected with the flood. I don't know. Maybe okay. So before we start with this example, okay, short transmission line. I hope you have already watched the pre-recorded YouTube video about this transmission line. I think all the videos contain the short transmission line and also the medium transmission line. Okay, but before we proceed with this example, I just want to highlight something. I hope you already know that our load usually for the transmission line, for example, this is your resident home, okay, and then you have the transmission line, okay, where you have a pole here, electrical pole, okay. So this one is actually A, phase B, phase C, and also neutral point, okay. And usually for single home, it will fed by a single one line from phase A and another line from the neutral, okay, and the other one is actually earth, okay. So that's why you have three pin, okay, which is earth, life, and neutral. So this life is actually referring to this uh, either phase A, phase B, or phase C, okay. So maybe other house it use phase B, okay, it use phase B and neutral point here, okay, and the other point is actually earth, okay. And since you have A, B, C, and neutral point here, so meaning that from the transmission line we have a generator, three-phase generator, okay. So the load connection should be Y connected, okay, Y connected, and then usually we have this another wire which is neutral point, okay, neutral. So that's why we have three-phase four wire system, okay. Okay, so why I'm explaining this, because it is actually related to the power transmission line, okay. So for all the example inside our notes here, okay, I have already explained in the pre-recorded videos, the voltage here is usually we are referring this value as V line, okay. It is not V phase, it is a V line. Same with our socket, okay, on power socket, which is 240 volt RMS, okay. This one is actually V line, okay. It's not V phase, it is actually V line. Okay, so in TNB or in our power utility design and so on, okay, so the voltage that we always talk about is actually for the three-phase system is always referring to the V line, okay, and the load, okay, the load that the type of load connected here is usually Y connected, okay, where I have already also explained in my pre-recorded video. So as can be seen here in my example here, I also highlighted this. Okay, in this topic, the voltage given is the V line and the load connection is a Y connection. Okay, so this is actually very important because usually in the question, we will not give you this information. Okay, it is very crucial to know about this. Okay, so we proceed with this example. Why I cannot this? I want to erase this. Okay, so actually for this transmission line, especially for the short transmission line meaning that the length of the transmission is lower than 80 kilometer. Okay, so if you are being given information like this, okay, 30 kilometer or lower than that, lower than 80 kilometers, so meaning that it is a short transmission line. So for the short transmission line, the modeling, okay, for analysis, we always do the modeling, okay. So for the short transmission line, the model is a very simple, which is consisted of resistor, internal resistance. This is actually represent the internal resistance of the cables and so on. And then we have a single inductor, okay. Okay, where we have the voltage sending and another one is the voltage receiving. Okay, so this is a three-phase system. So, but we assume that the system is a balanced system, meaning that all the voltage and the current are equals for all three-phase systems. So, meaning that we can simplify our analysis by using a single phase equivalent representation. So meaning that this is a single phase equivalent. So meaning that all the voltage here is a phase voltage. Okay. So the current here is also a phase current. The same current here is also a phase current where IS phase is equals to I receiving. Okay. So IS is sending while R is actually receiving. Okay. So it's very simple and straightforward. Okay, and for the voltage transmission line, we always there are two performance parameters that we always want to analyze. The first one is the voltage regulation. Is there any voltage different? Okay, when we, for example, uh, we want to see is there any voltage drop before the terminal is loaded or after without loading and with loading. Okay, usually for a good transmission line, the voltage, the difference is very small. Okay, so this is the first performance parameters that we always want to analyze. The second one is about the efficiency. Okay, for the voltage regulation, it's actually the difference between voltage receiving during no load minus V receive during full load over VR, if not mistaken, um, eh, oh tak ada kat sini eh. If not mistaken, this one is actually full load. If not mistaken. So this is your voltage regulation. And then for the efficiency, is actually the power output over the power input. Okay. So this is actually the question that will always be asked. Okay. And this is actually the question that will be asked in your test too. Okay. So this question is straightforward. It's actually the question is not related to the voltage regulation and efficiency. So the question is calculate the current and the voltage at the sending end of the line. Okay. So what you need to do is actually it give you the information here. Sorry, I think I need to erase this one first. Okay. So a 30 kilometer three-phase system, 50 hertz transmission line is transferring power to a 500 kilowatt, meaning that the load right now is a three-phase. So this one is actually three-phase power, 500 kilowatt with a power factors of 0.8 leading. Okay, meaning that the current is leading the voltage. Okay, what it means is that the load right now is a capacitive load. Okay, because it is leading. And the load voltage is 10 kilovolts. So meaning that VR line is given, which is 10 kilovolt. Okay. And the information given here is the resistance and inductance, which is 0.1 ohm per kilometer. And for the inductance is 0.424 millihenry per kilometer. So what you need to do is actually to get the R total. So R total is 0.1 multiplied with the length of the transmission line. And this one you need to have to convert into the reactance first. Okay. So you need to multiply omega L multiply with 30 kilometers to get the total reactance. So that is the first step that you need to take. Okay, calculate the R total and X total. Okay, and the next one is actually to convert this into V phase. Okay, so we know that for Y connection, okay, Y connection, the V line is equals to square root 3 V phase, right? So V phase meaning that 10 kilovolts over square root 3. So this is your V phase. Okay. So I have already calculated it for you. So the R total, which is 0.10 multiplied with 30 kilometers, so you will have 3 ohms. And the X total, so this one is omega 2 pi F multiply with the inductance and then multiply with the 30 kilometers. So you will obtain J 4 ohm. Okay, positive J because this is inductor. Okay, so the total impedance is 3 plus J4. So I give you mark if you obtain these values. Okay, and then next is actually the conversion of the line voltage into the phase voltage. So which is 10 kilovolt over square root 3, which is will give you the value of 5.77 kilovolt. Okay, but the angle is not there. Okay, the angle is not given. And please be noted that for this transmission line topic, the VR phase will be always be used as the reference. Okay, because for all the parameters, voltage or line, we always have some parameter that chosen to be the reference parameters. Okay, so for this transmission line topic, the receiving end voltage, phase voltage will be always the reference. So that's why I put angle 0 here. Okay, because we are phase is the reference. Okay? Understand? Okay. So I think this one is the fundamental. Is the fundamental uh, information that you need to calculate first before we proceed with the next step, which is the current. Okay. So right now, after you have obtained the total impedance and also the voltage phase, okay, next is actually to answering the question, which is the current. Okay, so we use the information which is have been given by the questions, which is the three-phase power is 500 kilowatts. Okay, so for the three-phase system, 500 kilowatt, and for the equation for the three-phase system is 3 multiply with VR phase multiply with I phase. Okay, this is R phase and I phase is a single phase. Okay, cos theta. Okay, so after you calculate it, so you will obtain 36.10. So from here, you will obtain only magnitude only, which is 36.10. How about the angle? So how I decide what is the value of the angle? So actually the angle is actually the inversion of the power factor, which the power factor is 0.8. So the inverse cos, I will obtain 36.86 degrees. Okay, but it is positive or negative, so it depends on the leading or lagging. So if the power factor is leading, meaning that the current is leading the voltage. Okay, so right now, what if you not understand? Okay, let's try to do this phaser. You know that VR is our reference, so this is my VR. Okay, since the question said that the power factor is 0.8 leading, meaning that the current IR is actually leading the voltage, right? With an angle of the power factor, which is 36.86. So as you can see here, so this VR is actually 0 degrees, right? Because the VR is the reference. So since IR is leading, since the power factor is leading, so that's why I give positive 36.86, meaning that it actually leads the voltage. Okay, I hope you understand this. Okay, so this calculation of current didn't give you the information about the angle. It gives you only the magnitude. The angle is actually comes from the power factors, and whether negative or positive, it depends on whether the power factor is leading or lagging. So usually for lagging power factor, so the angle will be negative here. Okay, why negative? Because if the power factor is lagging, meaning that you have this one is a VR, which is your reference 0 degrees. Lagging meaning that the current is lagging the voltage. So this is your IR. So since this is 0, so meaning that it should be at negative 36.86, right? Okay. Okay, next. So I think this one is the answer for the first questions. Okay, because I phase is actually your I is actually equals to your I ascending and I receiving n. Okay, which is 36.10 with an angle of 36.86 degrees. The second question is the voltage at the sending end. So we know that already, which is very simple and straightforward. which is this one is VS V sending, and then this is your VR. So this is your R total, and this one is your X total. So, and then this is your IS total. So from here you can use the KVL. Okay, the KVL. So we know that for this one is actually this. So you can just use KVL. Okay. So the Vs is equals to the voltage drop across this one plus the voltage sending. Sorry, the voltage receiving. Okay. So all the information have been calculated, which is the current, the total impedance, and the VR phase. Okay. Please be noted the angle is 0. Okay. 0. So finally, you will obtain this one is the values of Vs phase. Okay. So usually we will convert it back into the line values. So what you need to do is just uh, convert back into the line to line parameters. Okay. So just multiply with square root 3, and the angle should be um, add up with 30 degrees. So you will obtain this one as a 10 kilovolt with an angle of 31.79 degrees. Okay, so why need to add up 30 degrees back? Because we know that the relationship between V line and V phase is like this: square root 3 V phase, right? So after you obtain the V phase, so to convert back to get the V line, so you need to multiply with square root 3, and the phase must be at with 30 degrees. Okay. Okay, so if there is no questions, then we proceed to the second example. This one. This one. Okay. Okay. Maybe we take a break about maybe 5 minutes. Okay. 5 minutes. Okay. So we come back at, I think, 11:30. Okay. So you can either exit first to save your data, or you can remain in this room. Okay. So at 11:30 we will start. Okay. So for those who may not have enough time to read this first, so I think I give you time to read first the questions, and then to go through the solution first. Okay, this is actually come from the final exam, the previous final exam. Okay, so 5 minutes. Okay, break. Okay, so we resume our class. So this is also an example of the short line transmission line. A short transmission line. Okay, a 78 kilometer, three phase, 50 hertz transmission line is transferring power to a 3 megawatt load with power factor of 0.95 lagging. The load voltage is given 33 kilovolt. given the resistance and inductance of the line per phase is 0.05 ohm per kilometer and 0.255 millihenry per kilometer respectively. Calculate the voltage regulation VR of the transmission line. Okay. So actually the voltage regulation is to see the performance, whether there are a lot of voltage difference between when it is loaded or without loading. Okay, so the equation for the voltage regulation will be given like this. Okay, I think you need to memorize this one. VR no load minus VR, the voltage value at the receiving end during full loading over the VR during full loading. Okay. So, but first, what we need to do is to convert and to calculate all the impedance, the total impedance, and so on. Okay, so given right now the VR is actually a V line, so as given here. And since we know that you need to convert, okay, you need to convert because we are dealing with a single phase equivalent circuit right now. So R total and X total, and this one is your VS phase, and this one is your VR phase. So you need to convert this one. So converting this, you will obtain 19.05 kilovolt, and the angle must be set to 0 because VR phase is the reference. Okay. Next is actually to get the current. Oh, I forgot to mention in the previous example, since the load is actually a Y connection load, okay, so meaning that your IR phase is actually your IR line. Okay, so that's why you don't need to do any conversion. Okay, so from this equation, which is you know that the three-phase power is equals to 3 multiplied with V phase multiplied with I phase cos theta. Okay. So from this equation, or you can also use this equation, which is square root 3 V line I line cos theta. So in this example, I use this one. You can use this one or the first or the second one. Okay, it's up to you. But please remember, if you are using the first one, this one, the V use must be V phase. And if you are using the second one here, okay, the use must be V line. Okay. So for this example, I'm using the second one. Okay. So since I using the second one, so meaning that I use the VR line, which is the 33 kilovolts instead of this one. Okay. So you will obtain 55.25 ampere. So if you are not convinced, so you can try right now. So we are using the first one. Can someone just calculate whether you obtain the same answer? Let's try the first one by using the first one. So now 3 megawatt, okay, is equals to 3 multiply with the V phase. V phase is 19.05 kilovolt. Okay, multiply with the current that we don't know. We want to obtain this one, I phase, multiply with the power factor, which is 0.95. So from here, I will obtain my I receiving phase is equals to 3 megawatt over 19.05 kilovolt multiply with 0.5. I should get the same answer, which is 55.25 ampere. Okay, can you calculate? Verify it for me. 3 megawatt over 3 over 19.05 kilovolt over 0.95. Okay, you should get the same answer, 55.25. So you can either use the first or second equation, but please be remember, if you are using the first equation, the voltage must be V phase. Okay, so right now the current here is, since the load is actually Y connection, so it doesn't matter. Okay, so this value is actually your I phase, and this value is also your I line, because for Y connection, phase current and line current are the same. But right now, the value that you the current here that you obtain is only magnitude, only. Okay, so how to get the angle of the current here? The angle. So you need to have the angle. So the angle, as mentioned before in the previous example, you can use, we can get it or obtain it from the inverse power factors, which is the cos inverse of 0.95. Okay, which is uh, 18.19 degrees, but it didn't give you whether it is positive or it is negative angle. So the positive and negative angle is depends on the power factor, whether the power factor is leading or lagging. So if the power factor is lagging, so please put negative here. So that is how we obtain negative sign here. Okay, so right now the complete current values is 55.25 with an angle of negative 18.19. Okay, so so we have obtained the current, which is the phase current here, and then after that calculate the standard one, which is to get the Z total. Okay, I hope you know how to calculate the X. Usually the X, the student will always have problem with X. Okay, so calculate, so this one is should be positive J, 6.248. So the total should be 7.36 with an angle of 58 degrees ohm. Okay, so since it's shorter than 80 kilometers, so it is a short transmission line. So this is the model. Okay, for medium transmission line, the model is different because the effect when you have a transmission line that is longer than 80 kilometer, there will be effect of the capacitor. Okay, so that's why. So the first question is the voltage regulation. As mentioned before, you need to memorize this. Okay, so usually VR no load is always higher than VR full load. Okay, because you haven't yet connected to the load, so the voltage should be higher. When you connect the load, you will actually see that there are some voltage drop. Okay, so that is how we want to see the performance of the transmission. Usually the transmission line that is very good, the voltage difference is very small. Okay, meaning that the voltage drop in through the line is very small. Okay, so based on the short line model here, so if you see that here, when you VR is open circuit, which is no load condition, you will see that the current is zero. Okay, the current is zero. So when the current is zero, meaning that there is no voltage drop across this impedance, so meaning that your VR no load is equals to the voltage sending. Okay, so that's why based on the short line model, we will assume that or we can conclude that for the VR no load values, it is equals to Vs. Okay, so what is your Vs? So you need to use these values. Okay, so Vs is equal to I R Z plus VR. So you obtain the Vs, which is in phase voltage. Okay, and the VR full load is been given in the question, which is 33 kilovolt, right? But this one is the V line. So you need to convert into V phase. So V phase is 33 over square root 3. So you should get 19.05 kilovolt, which is we have already calculated earlier. Okay, so this one is 19.36 only magnitude, and this one is 19.05. So you can see there is some voltage difference. Okay, because of this is the difference is because of the voltage drop across the resistance and also the inductance. Okay, so you use this, insert all the values. Finally, you will obtain that the voltage regulation is around 1.6 to 7%, which is very low. Okay, so there is no standard which one is good or not good. But usually, if the percentage is very, very small, then we assume that the transmission line is okay in terms of the voltage regulation. Okay, extra calculation or extra question is actually to get the efficiency. Okay, so the efficiency, the general equation is like this, so very simple and straightforward. P out over P in. Okay, so for the short line, there is no problem in for this one, I think, because as you can see, you just use the equation here. But we already know that for the short line, the IR and IS is actually similar. So that's why we can delete this. Okay. And then square root 3 is also we can delete. So the only parameters that affect the efficiency is the value of your VR, the value of your Vs, the cos theta R, and also the cos theta S. So what is the cos theta R? So cos theta R, as mentioned here, is actually the value of angle difference between the VR, voltage angle, and also the angle of the current. So we know that the voltage receiving end here, we use as a reference, right? So that's why the angle is 0. Okay, while the angle of the current is negative 18.19. So by using this formula, you will obtain that my theta R is positive 18.19. Okay. And to calculate the the theta S here is actually the difference between the voltage sending minus the current sending angle. So from the calculation, the angle of the sending voltage, which is we calculated earlier, which is this one, right? 0.77 degrees. So minus 18.19, which is because current IS is equals to IR, right? So that's why the angle is actually same. Okay, so from this we calculate, we have obtained that the theta S is 18.96. So from there you substitute all these values uh, in this equation, you will obtain that the efficiency is around 0.988 or 80 sorry or 98.8%. Okay, any question? I think I'm very fast here. I hope you can follow me, but
Question.
it's okay. I think it's actually recorded. I think the main thing that you need to focus is actually to obtain the value of this theta R and also theta S. Okay. So what is theta R is actually the different angle between the voltage R and also the current R, while the theta is actually the difference between the voltage sending and the current sending. So that's all. Okay. Okay. If there is no any questions, I think this example is enough for you to prepare for the second test. For your second test, it's not very difficult. I think for the transmission line, it's just very straightforward. And if you can understand these two examples, the first one, the self-assessment, and then also this one. So I think you have no problem on answering the question, okay? Because it is straightforward. Even though, but as you can see, even though this question is straightforward, this one, your test too, with the answer, the question will be like this also. But even though it is straightforward, there are some parameters that need to be carefully calculated. For example, for the voltage here, okay, the angle of the current, the angle of the voltage. So you need to be what you call, be more in precaution mode, okay, on selecting whether it is negative angle or it is a positive angle. So it's up to you, need to actually understand the question in detail. Okay. So I hope my explanation can help you on excelling your second test, because from the first test, the spectrum, okay, of the student inside this section is quite broad. Okay, it's quite broad, where some part of you can actually answer the the test one which is a very good, and some part of you are what you call average students, and there is also a group that student that is under very low marks there. So the spectrum is quite broad. Okay, so it's quite difficult for me to handle the class. Okay, so I don't know whether my teaching method here is can try. I'm trying to tackle all the spectrums. Okay. Okay. So if there is no questions, so I think we can dismiss this class. And this one I will upload in my YouTube channel.